Hello and welcome. Thanks for joining us today. My name is Nathan Tabor and I'm a Senior Product Manager here at AWS working on the Containers team. I'm joined by my colleague Massimo who works on our team, and today we're going to be taking a first look at how you can use Amazon Elastic Kubernetes Service to run your Kubernetes applications on AWS Fargate. Our mission on the EKS team is to make AWS the best place to build and run applications using Kubernetes. Our goal is to remove the undifferentiated heavy lifting that you have to do to get new ideas off the ground and out the door, as well as make it easy to optimize your existing applications in the cloud. There's a few guiding principles for how we do this with Amazon EKS. First, we build to support production workloads from any size of customer. From startups to the largest enterprise workloads, you should be able to start an EKS cluster and have it just work. This is so important to us that we offer a 99.9% uptime service level agreement for every cluster. We've learned a lot from running production services at cloud scale on AWS, and we bring this experience to bear with how we run Kubernetes for you. Second, we think that native Kubernetes features and tooling should work seamlessly with EKS because we're committed to running upstream Kubernetes. Our customers tell us that this is critical to making EKS useful and appealing, and we think they're right. Third, being upstream means being good community citizens. Our team has spent a lot of time contributing bug fixes, security patches, and tooling improvements to the community. We're constantly listening to customers, building and refining open source projects that improve the experience of Kubernetes on AWS. And we are on AWS after all, so it's super important to us that along with the flexibility of the Kubernetes API, you get the power of AWS infrastructure. And this means integrations to the things you need to run your applications should just work, from storage to networking, security, identity, compliance, logging, auditing, databases, routing, ingress, and most importantly, compute. Our vision is that you can have everything you need to build and run your Kubernetes applications in a single place. You can create a cluster with a single command that includes all the compute resources, tools, and control that you need to run your application. We believe in smart automation that lets you take advantage of the building blocks that you need to build your applications without the ones you don't. And we'll always bias towards giving you the tools that you need with the right level of automation that lets you build faster. This isn't something we're going to achieve overnight. We've actually been at this for years, right? So several years ago, we saw customers using Docker on AWS, running containers themselves directly on EC2 virtual machines. And this is something that our customers were doing on their own, in their own accounts. And that's everything above the line here. We wanted to make this easier for customers. So in 2015, we launched Amazon ECS, our native AWS container orchestration service, which lets you launch containers onto a cluster of EC2 instances. ECS is managed by AWS, taking the need to run and decide when you start and stop your containers and how to manage your cluster out of your hands. So because this is managed by AWS, it's below the line. And in 2017, we added AWS Fargate support to ECS. Similar to how we noticed customers running Docker on EC2, we started to see customers running Kubernetes on EC2 virtual machines. And these customers, many of you, told us that you wanted an easier way to run Kubernetes on AWS. So in 2018, we set out to make this easier for you. We launched Amazon Elastic Kubernetes Service, or EKS, as a managed control plane for Kubernetes clusters on AWS. And that was phase one of EKS. So Kubernetes makes it easy to package and deploy your applications, but there's still a lot to do when you run your cluster. In addition to managing all of your containers, you still have to think about the infrastructure, things like virtual machines, autoscaling groups, and cluster autoscaler. For a lot of people, this means using Kubernetes is actually more complex, not simpler, than just running their applications directly on virtual machines. So for us, a managed Kubernetes control plane was just phase one. Phase two is removing the undifferentiated heavy lifting of managing the compute resources for your cluster. And we announced one of the flavors of removing this need to manage compute resources this fall 2019, Amazon EKS Managed Node Groups. This is automation that makes it easy to start your virtual machines for your cluster in your account. Now, this is EKS creating resources in your account. So these managed node groups are effectively living between the lines. They're managed by AWS, but they're ultimately owned by you. And recently, today, we've been really excited to announce that you can run Kubernetes pods on AWS Fargate, which is a serverless compute engine for containers on AWS. So we designed Fargate to make it easy to build and run your applications in the cloud. We want to give you the smart building blocks, the things you need to build and run your application without having to worry about complex configuration or managing multiple layers of infrastructure. Fargate gives you everything you need to run highly available, fast-scaling Kubernetes applications on AWS. We've carefully built this integration between EKS and Fargate to work in a way that gives you the power to run serverless Kubernetes containers while continuing to work with existing applications. You don't need to change how you've defined your Kubernetes applications to have them run on Fargate. You just tell EKS which pods you want to run, and they'll start on Fargate instead of EC2. Pods launch quickly, and they run automatically across multiple availability zones. There's no need to set up cluster auto-scaling. You just tell Kubernetes how many pods you want to run, and Fargate will handle provisioning the right amount of compute to run them. Fargate works with a horizontal pod autoscaler, which tells your cluster to run more pods when your application needs to scale. But it also works with the Kubernetes vertical pod autoscaler, which can request more or less resources for pods based on what they actually need to run. And with Fargate, you only pay for the resources your pods request when they run. This changes the game for how your applications run on AWS, meaning that every compute that you run is compute that you actually need. There's no need to over-provision or pay for resources that you're not using. Before today, Fargate only works with ECS, so you may be familiar with it in that context. But we see Fargate as a general-purpose compute platform for containers on AWS. We've built and will continue to evolve Fargate in its integrations so that the only differences are driven by the particular orchestrator that you're using and that orchestrator's API. Beyond that, our goal is that Fargate will behave the same. So now my colleague and friend Massimo is going to take you on a tour of EKS and Fargate to show exactly how Fargate works with the Kubernetes cluster and discuss some important things that you need to know as you get started using EKS with AWS Fargate.
All right, thanks, Nate. In the next few slides, I'm going to talk about how these actually work and some of the internals. Before we get into the weeds, let's level set the audience and let's talk a little bit about how Fargate works and the principle behind Fargate. So this is a very high-level slide about what happens when you ask your orchestrator, it will be EKS in this example, to deploy a container on an EC2 instance. So imagine that you are a user, an EKS user, and you're going to ask your control plane to deploy a container on EC2. What happens in this case is that the EKS control plane is going to deploy the pod on your EC2 instances that live in your account. So that would be the data plane that Nate was alluding to before. And it's going to attach that pod to your own VPC. Those EC2 instances that you see on the right-hand side are either managed notebooks or unmanaged EC2 instances. It doesn't change anything because they all run in your account. One of the drawbacks of this setup is that you have to manage that capacity. So you have to make sure that your autoscaling group cooperates with cluster autoscaler for scale in, scale out, training of the nodes, and all of those things. Not easy to do. Fargate changes this dynamic radically. So instead of having EC2 instances running in your account, Now, those pods and containers that you ask the control plane to deploy on Fargate will be deployed on the Fargate fleet. So basically what we do is when you launch a container or a pod on the Fargate fleet, we're going to instantiate that pod on one of the VMs or micro VMs that is part of the Fargate fleet, and we're going to still attach that pod to your VPC. So from a functional perspective, nothing changes, but the good news here is that you don't have to manage capacity in your account to do this. So that's at the very high level the principle behind Fargate. As we started to socialize this with customers, a lot of them were confused about the difference between Fargate and managed nodes or managed node groups. So this short table is going to illustrate some of the key points where Fargate is different from managed or unmanaged nodes. So the first thing is that the unit of work and the unit of charge for Fargate is always going to be the pod. The pod is the only thing that you need to care about. For managed worker nodes or node groups and unmanaged nodes, you always have to deal with both the pods that you're deploying that describe your application and the EC2 instances that are running in your account. Also, the unit of charge is very different. For Fargate, it's always going to be the pod. You're going to pay for the pod that you're deploying on Fargate. Whereas for traditional managed or unmanaged EC2 instances, you pay for the EC2 instances that are running in your account. The other important thing when it comes to the difference between Fargate and managed or unmanaged worker nodes is the host lifecycle, which includes, the AMI that you're going to pick for running those EC2 instances. For Fargate, this is just not visible, right? You don't have to have to manage or lifecycle those EC2 instances because we do that behind the curtain for you within the Fargate fleet. This is where the managed and unmanaged worker nodes are a little bit different, where the unmanaged worker nodes are pretty much on you in terms of management, whereas for managed worker nodes or node groups, we take on some of the burden that involves managing those worker nodes. So for example, what we do with managed node groups is we update the Kubernetes agents that run on that EC2 instance, and we do this in collaboration with the control plane update, for example. However, having this said, as you can see from the table, you can still SSH in your EC2 instance even with managed node groups. So it's not like with Fargate where there is no visible host at all. Last but not least, it's the host-to-pod relationship. Typically, when you run EC2 instances in your account, either managed or unmanaged, what happens is that you're going to deploy more pods on a single EC2 instance. Whereas for Fargate, the model that we use is always going to be a one-to-one. Basically, what happens is that when you try to deploy a pod, we source dynamically a VM or micro VMs from the Fargate fleet, and we deploy that single pod on that VM or micro VM. So to summarize, this is what you have been doing up until now with EKS. So that is the EKS control plane, and those are the pods that get deployed to a traditional container data plane. Be it managed or unmanaged, it doesn't make a lot of difference. These are a group of EC2 instances that are running in your account that are scaled using an auto-scaling group and that are managed by either you, the customer, or us, if it is the managed node groups. What we have announced at re:Invent is the additional possibility for the very same control plane to deploy to the AWS Fargate fleet, to what we refer to as the serverless container data plane. This is one of the options that you have available, what I'm referring to as mixed mode in this slide. However, one of the possibilities for you is to use a Fargate only data plane. So basically, you only deploy an EKS cluster in our managed account to deploy only on AWS Fargate. Before we get into the weeds of how this actually works, what we wanted to do is to show you a little bit of a demo of how this works. So this is a shell that has some client commands like kubectl, for example. These already configured to point to an EKS cluster that I properly configured for the purpose of this demo. So if I start to explore this cluster, you will see that there are no pods running on this cluster, right? Similarly, if I go and I explore the nodes in this cluster, there is actually no node that is available in this cluster. And you can tell from looking at the EC2 console where there is actually only one instance, which happens to be the Cloud9 environment that I'm using as a client to interact with my cluster. So as you can see, there are no worker nodes, either managed or unmanaged. There are no EC2 instance running here. So the other thing that I could do is I could explore the namespaces that I have available, and there are the standard default kube system and other namespaces that EKS deploy when the control plane comes up. The next thing that I'm going to do is I'm going to deploy a couple of YAML files, a couple of pods. Nothing really special. The first one is an Nginx. It's a standard deployment, one replica of an Nginx image. As I said, nothing fancy. It's just for the purpose of demonstrating what happens. So I have just deployed one in the default namespace. What I'm going to do is I'm going to create another namespace. I'm going to call this demo, for example. And I'm going to actually deploy the very same YAML file in this demo namespace. It is the very same YAML file, so the very same pod that is being deployed in those two namespaces. If I'm going and query again my system, I see a couple of things, a couple of interesting things. So the pod that has been deployed in the default namespace, it's running already. The pod that I'm deploying into the demo namespace is still pending. And there is a reason for that. We can stay here and query the system, the cluster for whatever we want to do, but this will not come up. And there is, as I said, a reason for this that we will explore in a second. Once I have my pod in the default namespace up and running, what I can do is then I can actually interact with my pod in very traditional way. Like I could, for example, exec into this pod. So if I do this, I can get into the pod and do everything that I would usually do when I'm execing into the pod. So just to be clear, if I query it again, this has not come up. It's still in pending, and we'll see why in a second. Even more interesting, to the point that I was trying to make before we switch to the demo, is that if I query now the host or the node, I'm going to see something interesting. You remember there was no node running attached to this cluster. Now there is one. It's this virtual node that we have sourced from the Fargate fleet in order to be able to run the pod that shows up as running right now. The interesting thing here is that if I go back to the EC2 console and I refresh this console, there is no EC2 instance that I can see. So that EC2 instance that is baking that pod that just started lives in the Fargate fleet. I don't get to see that EC2 instance. So let's explore why the pod that I deployed in the demo namespace didn't start up. So this is the cluster that I'm using. It's a cluster called Fargate. I can get into this cluster. The very first thing that I see here is these node groups, right? This is what Nathan said we announced recently, and it's the ability for you, the user, the customer, to deploy EC2 instance that we would manage for you. So as you can see, there is nothing here which reflects what you see in the EC2 console. There is no EC2 instance. What we launched at re:Invent, and what this Fargate integration looks like is this notion of Fargate profiles. So now you have an option of adding Fargate profile within the EKS cluster. And notice that I have already created previously a Fargate profile called default namespace. And this should hint you about what was happening in my demo. Right? So the Fargate profile, among other things, allows you to intercept the pods that are coming in into EKS to be able to match them and decide whether or not they should go to the Fargate data plane. So the way that works is that through this pod selector, you can specify a namespace and optionally additional labels so that you can say if there is a pod coming in a particular namespace that matches what I have defined in my Fargate profile, take that pod and send it to Fargate. This is actually what happened in my demo. Since I only have one Fargate profile that has one single namespace called default, all pods coming in that are being deployed into the default namespace are going to be sent to Fargate, whereas pods that come in other namespaces are not going to be catched by this role, and they will just stay pending because there are no EC2 instances that would allow the scheduler to start those pods on standard EC2 worker nodes. That's pretty much how it works in practice. And now let's go back to the slide to get into some more details about how this works. So if you think about Amazon EKS, there are two things about Amazon EKS. Obviously, there are the Amazon EKS native AWS APIs. Those are the APIs or CLI commands that you will use to create the cluster, update the cluster, and do all things related to the lifecycle of the cluster itself. And then you have the Kubernetes APIs, those that will allow you to do apply, autoscale, expose, exec, and everything that you would normally do with a Kubernetes cluster. So for this integration to work, what we have done is we have added an additional API that allows for the Fargate profile that we just discussed lifecycle, so you can create, delete Fargate profile, so that match that I was alluding to happens. This is an example of a Fargate profile. This is slightly different from the one that I was using, just because, as you can see, there are more selectors in this one. So I have default namespace, I have chip system namespace, I have another custom namespace called my namespace that has also labels. I don't want to get into the very details about how the selection process works, but I want to use this example to call out a couple of things, and in particular, the main reason for which we use Fargate profiles. The main reason, one of the two main reasons for which we use Fargate profile is for introducing this notion of the matching that we have just discussed. So through this selector, this is the way that we match what's coming in from what needs to go to Fargate or to a standard EC2-based control plane. So this is the very first reason for which we need to use Fargate profile. The second reason for which we need to use Fargate profile is to give a context to the pod that is being deployed on the AWS platform. So everything that exists on the AWS platform, including the Kubernetes pod, needs to have an AWS context. The AWS context may point to which subnet can I use to connect that pod, and this is where you show this in the Fargate profile. Or the other thing is, what execution role should this pod have? So think, for example, how can I make sure that this pod, and the kubelet in particular, is able to grab a Docker image from ECR, for example. That is what the pod execution role is for. I can associate a set of policies to my pod so that my pod can behave in a certain way within the AWS platform. So to recap, the Fargate profile, we have to introduce Fargate profiles for two things. First of all, for the matching with this selector, and the second reason is to give the pod a context to run within AWS. So let's make a practical example of how this works. So this is somewhat similar to the demo that you had just seen, but a little bit more complete. So in this example, I have an EKS cluster that has attached both a set of worker nodes, managed node groups, for example, as well as it has a Fargate profile that enables you, the user, to deploy to Fargate. So the way that this integration works is through a number of extensions that we created following the traditional way that you would extend a standard Kubernetes cluster. So through custom scheduler and through mutating webhooks that live and run on top of the EKS cluster that we just deployed. So let's make an example here. So you, the user, come in and you want to deploy a pod in the prod namespace, and this pod has a label that says spec equal blue. So what happens when this pod comes in is there is a webhook that intercepts that pod and is going to ask the EKS control plane, is there a Fargate profile that matches this configuration for namespace and potentially labels? As you can see from the left-hand side, there is indeed a Fargate profile that matches this. So there is a selector that says everything that gets deployed to namespace prod and has spec equal blue goes to Fargate. That's kind of the meaning of the Fargate profile. So what happens next is that there is a mutating webhook that is going to take that pod and the pod spec and mutating them to insert the profile name and the name of the custom scheduler that we're going to use. The custom scheduler is a scheduler that we built that runs side by side with the traditional out-of-the-box Kubernetes scheduler, which is responsible for sourcing that VM and doing the magic that we have just discussed so that this pod gets deployed on the Fargate fleet. Another example is I come in and I want to deploy a pod in the test namespace. Same thing. There is a webhook that is going to take that pod, ask the EKS control plane, is there a match between this pod spec and any Fargate profile that you have? The webhook is going to say, no, there is not a match here. I'm just going to send this to the standard Kubernetes scheduler for the Kubernetes schedulers to schedule this pod on worker node. This is actually what happened in my demo. When I deployed my pod in the demo namespace, since there was no EC2 instance running in my account, that pod will remain pending forever. If I was to deploy on the fly an EC2 worker node or a managed node group for that matter, the scheduler would recognize the additional capacity being available to the cluster in the form of EC2 instance, and it would start deploying or schedule that pod on those instances. So one of the first things that customers asked us when we started to socialize is do we need to change the specs of every single of our pods in order to take advantage of Fargate as a serverless container data plane? And the answer is no. Actually, if you paid attention to what we have just discussed, you can configure EKS to deploy to Fargate without even touching your pod spec. So the flow is that you run a pod on standard worker nodes, which is probably what you're doing already. You create a Fargate profile that matches the pod namespace and optionally labels. So you know what you're running, so you could create a Fargate profile that is able to catch that combination. Then if you kill the pod, that pod will restart on Fargate. This is a graphic illustration of what I just discussed. So you have the very same setup that I was showing you before. In this case, you don't have any Fargate profile. So imagine you come in and you deploy a pod in the default namespace. As we said before, the webhooks is going to query the EKS control plane for any match with the Fargate profile. There is no Fargate profile, so this will be sent directly to the scheduler for the pod to be scheduled on EC2 worker nodes. This is, if you have been using EKS, this is what happened up until this integration was available. Now imagine that in this very same situation, on the fly, you create a Fargate profile. And that Fargate profile says in the selector namespace equal default. In that case, if you try to redeploy the very same pod with the very same spec, so if you try to redeploy in the namespace default, what happens is that the webhook will still ask the EKS control plane if there is a match. In this case, there is a match because you have just created a Fargate profile that will generate that match. In that case, the webhook, the mutating webhook, will mutate the pod spec on the fly, will insert the profile name that is going to be used with the Fargate scheduler, the custom Fargate scheduler, and this pod, the very exact same pod that you were running on EC2 instances, will start running on Fargate. So now that we have a clear view of how the EKS control plane pick what needs to go on Fargate and what needs to go on EC2, we need to discuss how we size that pod. This is obviously a problem that was not real or did not exist when you were trying to deploy to EC2 instances, because at that time you were setting or you were picking an EC2 instance size that could run a number of pods depending on how they were configured. But now that we don't have any EC2 instance and we just need to run pods, what happens to the sizing mechanism? How do I size that pod? Everything that we're going to see in the next few slides is dual dimension. Everything that you're going to see here applies to both memory and CPU in parallel. So before we get into the weeds of how we do sizing, it is important to understand there are a couple of types of containers that could run in a pod. There are init containers. These are containers that typically prepare the environment. They come and go, meaning that if you have more than one init container, they are executed sequentially. The first one starts, it stops. The second container starts, it stops. The third container starts and stops, and so forth. And then there are long-running containers. Those are the containers that are doing meaningful work, right? Those are the application containers, if you will. So imagine that you have the first init containers, and each container that you're going to run in a pod has implicitly or explicitly set a couple of things: the limit and the request. And as I said before, this is bidimensional. For both memory and CPU, there is limit and request. Request is the amount of memory or CPU or and CPU that container need to have available to be able to run. If there is not that amount of CPU and memory on the system, it will not be scheduled. Limit, on the other hand, is how much capacity, CPU and memory, that container is allowed to use in addition to the request that it makes. So request, if you will, is how much I'm going to reserve on the lending system. Limit is whatever the capacity on the lending system is, how much that container can use of CPU and memory. So this is the first init container in my example. This comes and goes. Then there is a second init container that has different requests and limits. And then there are maybe a couple of long-running containers. Think about the sidecar patterns or anything that would require running more than one containers in a pod. So the logic that we use in order to size that pod is, first of all, we only take into account the request that each of those containers make when they start. The second thing is, since these are long-running containers that run in parallel, we add them to each other, right? So we add them together, and we get to a number. At this point, we take the highest number between all the individual init containers, because they run individually, and the sum of all the long-running containers. In the example that I've made here, that is the highest number. So we take that number, and that number has two dimensions, CPU and memory, and that is what we use to size this pod. Let's make another example. Imagine that you have this setup. You still have a couple of init containers. You have still a couple of long-running containers, and these are the requests. So again, we sum them. We sum the long-running containers, and we take the biggest number across all these three pillars that you see on this slide. So this may be unusual, maybe not very realistic, but this is how our logic works. In this case, the highest number is one of the requests of one of the init containers, and that is what we take to size this pod. So this, if you will, is yet another example where you have two init containers and four long-running pods. In this case, probably more real life. The aggregation of the long-running pod is what driving the sizing of the pod. So how do we get to an actual pod sizing? So we take that number. Remember, that number is two dimensions, CPU and memory. So we do everything that we have just said twice, once for CPU and once for memory. And then we go through the Fargate task size combination that we show publicly in our documentation, so that we can pick the right size for that pod. Actually, what happens here, I should mention that in order for all the Kubernetes mechanic to run inside that pod, including the kubelet and everything that needs to run inside that kubelet to allow it to show up as a virtual node inside my cluster, we also add 256 megabytes for those Kubernetes components to the size of the memory. This applies only to memory. So let's make like a real life example. If you had an aggregate of memory for all these running containers that is 1.6 gigabytes, what we do is to that 1.6 gigabyte, we add 256 megabytes, which makes it 1.8 something gigabytes. And then we pick the rounded up, the closest config rounded up, which for memory would be 2 gigabytes in our case. And we do the same for CPU in order to pick a size for the CPU as well. All right. Let's explore a little bit in detail what happens for networking and security now. In a traditional scenario where you have pods running on EC2 instances, basically what we do is we deploy typically multiple pods on an EC2 instance, and each of those pods get a secondary IP address from the ENIs that exist on those EC2 instances. So this would be the traditional scenario if you have been using EKS running on traditional EC2 instances, either managed or unmanaged. It doesn't make a difference. With the Fargate scenario, this is what happens. So because every single pod runs on a dedicated VM or micro VM from the Fargate fleet, every single pod has a dedicated ENI that it is attached to for that VM or micro VM. One thing to keep in mind in this case is that there is a security group that gets associated to all of those ENIs in the Fargate fleet in my cluster. So even though this model will allow in the future for more flexibility in terms of assigning different security groups to different ENIs, at GA, the way that it works today is that we are going to apply the very same security group to all of those ENI for simplicity and for avoiding customer to make misconfiguration on the system. Let's jump to load balancers configuration. Still networking related, but specific to load balancers. So the ALB ingress works as it would normally do. Just make sure that you use the latest version because we had to make some changes to accommodate the way that Fargate works. So make sure that you are using the very latest code for the ALB ingress, but this would otherwise work just as it normally does. NLB support is coming soon. So NLB support is not available at the time of this speech, but make sure that you stay tuned because we intend to support the NLB soon. CLB, or the classic load balancer, will not work. And this is by design because the classic load balancer assumes that there are EC2 instances as target. And because of the way Fargate works, there are no EC2 instances that the classic load balancer can point to. So the classic load balancer by design and by architecture will not work with the EKS and Fargate combination or integration. Before we close down, a couple of notions on storage. Storage options with EKS for Fargate. As of today, Fargate provides only local ephemeral storage to the containers running in the pod. This is a Fargate characteristic. It's not so much an EKS integration characteristic. Fargate only provides ephemeral storage for local containers. So basically what happens and what you could do is you could create and you could carve out some of that ephemeral storage for the time that the pod lives so that you can share that storage, ephemeral storage, among all the containers that exist inside your pod. Having that said, persistent storage or forms of persistent storage is certainly a frequent ask from customers that would like to run, in additional to stateless workloads, that would like to run also stateful workloads using Fargate. And we are definitely exploring what it is possible in this space. So stay tuned here because we want to make this happen, because there are lots of customers that are asking for this support, and we're working to accommodate that. Last slide before I pass the ball back to Nathan. EKS CTL. So as many of you know, EKS CTL is our preferred tool to stand up EKS clusters. And EKS CTL has added support for both Fargate and EC2 worker nodes. Obviously, make sure that you use the latest versions, because obviously previous version before this announcement did not support creating EKS clusters that did support Fargate, meaning EKS cluster with, for example, default Fargate profiles, for example. It is possible to create a Fargate-only cluster or a combination cluster that has combination of Fargate profiles as well as managed node groups, for example. So you can create mixed mode clusters. And EKS CTL takes care of some undifferentiated heavy lifting, like, for example, as I said, creating Fargate profiles that we do not create by default when you create an EKS cluster using our APIs, but EKS CTL can take some of that burden for you, and it will create a more opinionated setup ready to use. This is the easiest way to create a cluster with Fargate support. EKS CTL create cluster -- Fargate. It cannot get simpler than that. Having that said, I'm going to pass the ball back to Nathan for some latest news.
Thanks, Massimo. I'm pretty excited about this. It's an awesome feature, really nice experience to start running on Fargate. So let's actually recap some of the changes that Fargate introduces when running your pods. First, you no longer have to manage worker nodes, pay for unused virtual machine capacity, or use cluster autoscaling. You get VM-level compute isolation per pod and pod-level billing and reporting right out of the box. But Fargate is serverless, so there's a few things. Okay, actually, let me start that again, because I think that I went a little too fast. Okay, we're going to start that again. All right. Thanks, Massimo. I'm pretty excited about this. Awesome demo and really nice walkthrough. Let's quickly recap some of the changes that Fargate introduces when running your pods. So when you're using Fargate, you no longer have to do things like managing worker nodes, pay for unused virtual machine capacity, or use cluster autoscaling. Right out of the box, you get VM compute isolation per pod, you get pod-level billing and reporting. But Fargate is serverless, so there's a few things you can't do. Things like deploying daemon sets or running privileged containers. Also, today Fargate does not yet support stateful volume or file system-backed workloads, and it only supports application load balancing for pods. We'll be working to deliver more options for load balancing to Fargate pods in early 2020. There's also some limits that you should be aware of when you start using Fargate. We have a default regional limit of 100 pods and tasks per account, though you can easily have this raised, and each Fargate pod shows up as a node. So with Kubernetes in general, the community tests up to 5,000 nodes today, and we consider this to be the upper bound with Fargate. However, in the next year or so, we're going to be working closely with the community to improve the design of Kubernetes for nodeless, serverless workloads, and we'll be listening to our customers really closely for guidance on how we can improve the total size of clusters that you can run with Fargate. Also, the behavior of Fargate may be a little different than what you're used to with virtual machines. When you scale, Fargate will generally scale faster over longer scaling cycles, as each pod starts faster than a new virtual machine. However, if you're starting just 1 or 2 pods on Fargate, it may be slightly slower than starting a few pods on an existing virtual machine that's already provisioned and has spare capacity. And this is really part of the fundamental change that happens when we switch to delivering on-demand compute capacity for your pods. We're going to continue to invest to make it quicker and more seamless to scale your applications up and down as this product continues to evolve. So pricing for EKS and Fargate is unchanged. Each EKS cluster is just 20 cents per hour with a highly available multi-AZ configuration by default and a 99.9% uptime SLA. You only pay for the vCPU and memory resources requested by your pods with Fargate, and that's just the standard Fargate pricing for vCPU and memory per second. And today, EKS on Fargate is generally available for all AWS customers with new EKS clusters created with Kubernetes version 1.14 and above. We'll be expanding support to existing 1.14 clusters automatically over the next few weeks. And you can use EKS on Fargate today in Virginia, Ohio, Dublin, and Tokyo AWS regions, with more regions coming in 2020. So this has been an overview of how you can use Amazon EKS to run serverless pods on AWS Fargate. On behalf of myself, on behalf of Massimo, and the entire containers team at AWS, really appreciate you coming to the webinar today. And we have a few minutes here at the end where we can take some questions. Thank you very much.